they do not show up right. Okay. All right, so last time we were talking about how these energies, as you rotate between each other and you overlap these orbitals, well, they're going to repel each other, right? And so they're going to be resistances, right? Now, if it has a larger overlap, it's going to be a larger energy resistance, right? It's going to be harder to turn, okay? If it has a smaller overlap, less resistance, and so we can turn it with less energy. This is called the rotational energy barrier. It's going to be between two conformations. It's going to be the difference in the energy between the beginning conformation and the highest energy conformation. The molecule must pass through to arrive at the ending. So right here, they're all the same energies, right? And that's because they're all hydrogens, okay? And these right here are going to be those rotational energy barriers right there. And so we have to overcome those rotational energy barriers every time to get to the stable configurations. Okay, and so what we see here is that depending on the amount of energy that we have available in that system, is going to tell us how often that interchange is going to happen. Okay, you can in fact freeze the conformations and make it so you can't actually move between them easily by getting the temperature low enough. It's kind of an interesting thing. So in this case right here, what we would see is that this takes right here about 12 kilojoules per mole. So at this temperature here, the percent of molecules that we'd find at 12 kilojoules per mole is about 2%. So about 2% of the molecules at any given time would have enough energy to actually do that rotation. Okay? Okay, and so they'll overcome it and go over here, and that's going to be about 2% at any given time. All right, now, what happens after we start adding groups onto this, like CH3s and bromines? So let's go ahead and look at a bromine, because that gives us a nice clear label here. So this eclipsed configuration with the bromine, see how that's really, really high energy here? Okay, that's because bromines are really big, right? And so when they're over eclipsed, they're overlapping, they're going to repel each other very strongly, right? Now, when we get down here, this is going to be the gauche, okay? That's what that's called, where we have the staggered conformation, but the large groups are just one step away from each other, the 60-degree step. See that? So we have the 60-degree difference here. And so they're still going to interact a bit, aren't they? Because they're pretty big. And that means that we don't actually get to as low of an energy as we could have gotten. Now, the next one, these bromines are going to have to pass by hydrogens. So see how that barrier is much smaller, isn't it? Okay. And so that eclipsed form right there is going to be much smaller energy barrier. And then we come over here, and this is called the anti. Okay. This means it's going to be on opposite sides of each other. And so this is going to minimize the interference between these two bromines. They're going to interfere with each other the least, right? And so this is our lowest energy state. This is the lowest energy conformer. Okay. This is where these are opposite each other for the bromines. So if you look at this bromine here, it's on one carbon. This bromine's on the other. And they are on the opposite of each other. So they can't interact with each other at all, because they're on completely opposite sides of the molecule. Okay? And so that's going to have your lowest energy that's possible, because they no longer interact with each other at all. The only ones they interact with are the hydrogens that are nearby. Okay? Okay, notice that this one's symmetric because the molecule is actually symmetric right here. Everybody see that? And so you actually end up with another gauche that's just the -60 instead of +60. And right here, these actually loop back into each other. Those are the overlapping bromines again. Okay, that's the same thing. That's the 0 versus 360. Okay, so this is actually what that would look like in 3-dimensional. So here we have the gauche conformer. And this is going to be where they're just a little bit offset from each other. Can you see that? And see that those are going to interfere with each other the most. Okay? This is the anti-conformer, and this is where they're on opposite sides of the molecule of each other. So they're going to interfere with each other the least. Okay, so again, anti-conformations are going to be 180 degrees apart in a Newman projection. So opposite sides of the Newman projection. Gauche conformations are going to be 60 degrees apart in a Newman projection. This Newman projection angle we keep talking about, this is what's called a dihedral angle. Okay? That's actually what the dihedral angle is. Now, the gauche and anti-conformations are going to be conformers of each other. They're both stable, and so they would be stable conformations of this molecule. Okay? And they'd be the conformers for this molecule. Now, in this case, the two gauche conformers are the exact same. Okay? They'd be 60 and negative 60. They have the exact same energy. One is just opposite the other. Okay. Okay. Now, this right here again is that gauche. Remember, they're going to have what's called steric strain to the molecule. So when they're gauche to each other, they're going to have a little bit of overlap of those orbitals, right? A little bit of overlap of the electrons trying to repel each other, as we can see up here. Okay? And that's what's referred to as steric strain. Okay. Now, the anti to each other, they can't interfere with each other at all. The only thing they can interfere with is the rest of the molecule, right? So they don't have any relation to each other anymore because the rest of the molecules in between. Okay? And so they don't have any steric strain to each other anymore. Okay, now let's go ahead and look at that zigzag we were always writing out for all these carbon chains. What did you notice about the zigzag? What does that do to our carbons? So if we were to look down this bond right here, this carbon to this carbon, would that be gauche, eclipsed, or would it be maybe anti? Anti, yeah, they're on opposite sides, aren't they? Yeah. And so that zigzag we were doing, we were always doing the most stable conformer, weren't we? That's why we were just zigzagging it out. Okay? We were writing out the most stable conformer because those are all anti to each other, aren't they? Right? And that's why you did that. You didn't know it. It looked right because it is right. Which is always a good thing. Now, that's that zigzag conformation. Again, that's the all anti conformation. Is this the only conformer for this chain? No. No. There's going to be some portion of your molecules that's going to rotate around that single bond here, and this chain is going to come up like this. Okay. And so you'd get the gauche conformers on some of these as well. Okay. There'll be a small amount of them. Okay, so let's talk a bit about some 5- and 6-membered rings. The most common rings in nature are always going to be the 5- and 6-membered rings. You may recognize them from many, 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 many different structures that you've seen all around you in your life and in biology. Biology would be a big one. So right here, for example, ribose and deoxyribose. Everybody knows those, right? Deoxyribose DNA, ribose RNA. This is diamond right here. This is androsterone. Excuse me. Really needed some water. And this one's menthol. Okay. So by far and away the most common ring structures, 5- and 6-member rings. And the reason for this is something called ring strain. Okay. So most of the instability for the other ring sizes is due to this ring strain. And that's going to be the increase in energy that's due to the geometric constraints of that ring. So does anybody remember what angle that you typically want for tetrahedral bonds? 109.5, right? What happens when you have a triple 3-membered ring? What angle does that have to be? 120, right? It has to be 120. So 360 total. 120. And that means that you can't make 109, can you? You're forced to be in these 128-degree angles, and that means all of your bonds are experiencing strain. They're involved in this structure. Okay? And so this right here is actually the energy of that. So remember that you're going to have energy for being off of the 109.5, which is that ideal amount, assuming you have all carbons around. Now, cyclohexane actually has 0 ring strain, and that's the 6-membered ring. And if you look up here to cyclopentane, you see that it's 27 kilojoules per mole ring strain. So it's a relatively small ring strain. Okay, there is a ring strain though. Right here we have cycloheptane, which has about the same ring strain. It just doesn't happen to happen as many times in natural organic compounds. So there's other reasons to that one. Partially, it doesn't happen because it's not a common like size that would be produced from the compounds that are used in biology. But there's other reasons. Now, because the cycloalkanes consist of a carbon-carbon single bonds, we also are going to get torsional strain and steric strain. These are going to be those two major contributions to the ring strain. We're kind of summing up those two contributions as ring strain. Now, the third major contribution to ring strain is actually going to be angle strain. Now, this is going to rise when your actual bond angles differ significantly from your ideal bond angles, and that's what I was mentioning before. You're also going to have a overlapping, that they're too close to each other, and that's going to be your steric strain. And then your torsional strain, which is the torsional angle of these rings. Okay, so keep in mind, like a 3-membered ring, you can't actually make any sort of angle in it. It can only be a flat plane. Okay, and that planar is going to create this torsional strain to it. Okay, all right. So let's rank the following compounds in order from least ring strain to greatest ring strain. What do you think would have the most ring strain? What do you think would have the least ring strain? Okay. So we're going to go through, and basically it's the order of the size, isn't it? Okay. Now remember that that will then deflect and start becoming less stable as we get longer. Okay. Not a huge amount. Like the longer rings actually are more stable than like, you can't get longer rings that are usually less stable than like 3 or 4 member. Those are going to be your least stable ones typically. But the longer rings do destabilize after 6. Okay. Okay. And so least stable, that one right there, right? Second least stable. The 4-member ring will be the second least stable. 3-member ring, the least stable. Okay. Next least stable. 5, right? Then we go up to the 6. That's going to be your most stable. Okay. So remember all of these terms we've just went through, right? Okay. So don't forget those. Okay. Okay, we're going to start building off of that. All right, now, the cyclohexane, this has no ring strain. And the reason for that is, yeah, we've been drawing these rings like they're flat, okay? But in reality, these rings are not flat. Okay, when you if you use your model kits, you quickly realize that the rings are not flat, like immediately, right? And that's because when you build them, you'll go, oh, this doesn't flatten, except for the 3-member ring. That one flattens. Okay, so this one right here, this is going to be your cyclohexane, and what ends up happening is you essentially have no ring strain in this. It becomes very minimal, and that's because it can take on what's called a chair configuration. Okay, so this is what the ring looks like. Can everybody see that okay? One flap goes down, then you go into a plane right here, and then you go up. Okay, looks like a folding chair, right? Everybody see that? You have the footrest that goes down there, then you have your butt rest that goes straight, and then you have your headrest, right? Okay, so chair configuration. I know, chemistry mentioned it too. All right, so this greatly reduces its ring strain because you can essentially make tetrahedral normal bonds, right? And then not only can you do that, but you can reduce the amount of gauche conformer that you would have, and you can reduce the amount of the steric and torsional strains you can have. So you don't have a lot of overlapping. You're not forcing things to overlap. You're not forcing things to be in very unstable configurations. And this is what that looks like if you look down these two bonds here with Newman projections. Okay. And you can see this is why it does one above, one below. Is because then it can put the carbon up here for this one and the carbon down here for the other one. Okay. Which is going to minimize that steric strain that we were talking about before, right? And then we have basically the exact angles we expected, those normal like 60-degree angles. And that minimizes that torsional strain. Okay? And so we managed to minimize essentially all of the different strains. Okay. Okay, so let's go to the 5-membered ring. And so the 5-member ring is typically most stable in what's called the envelope conformation. Now, these rings, these are not the only conformations they can go in. But these are typically the most stable ones. Okay. And so this is the envelope conformation. We have a basically flat ring right here for the 4, and that comes up into a little lip of the envelope, just like an envelope for sending a letter. Okay. And this is what it looks like if you write it on a piece of paper. So it looks quite similar. Now what you'll notice here is this is not as stable as 6-member ring, and that source of instability here, we can't get that angle the normal 60 degrees, can we? And so that normal 60 degrees, we want to reduce that torsional strain as much as possible. We can't do it. It's just not possible to do. And so you get that partially eclipsed right there, and that's going to increase that energy just a bit. And that's that 27 kilojoules per mole. Okay. Okay. Now, this is cyclobutane. This is very unstable. As a little kind of story, I used to have to, so this is kind of stuff I did. My dissertation is like 700 something pages, and it's a textbook. And it involves 4, 5, and 6-membered rings. And we did a lot of research on like conformations and molecular structures and vibrational assignments. Anyways, so kind of a funny thing is like these 4-membered rings were just the hardest to get a decent yield and synthesized because you put something on them and they become unstable. You leave them in light and they become unstable and start reacting with each other. And so you have to like purify it in the dark. So it'd be like 12 hours of me sitting around listening to music and playing like a video game while I'm purifying my dang sample, and I'd have to do it completely in the dark at night so the dang light didn't get to it and destroy all my purified sample. And that's it being at liquid nitrogen temperatures. So liquid nitrogen temperatures, still, if I got light on it, it would destroy a large portion of my samples. And I would have these things, and we'd have to run them within hours. So I'd have to be up all night running these, getting the sample purified, synthesize it, and then all night purifying it, and then it'd be like 36 hours later, and I finally have all my spectra done. And so I have actually been 36 hours without any sleep whatsoever, in case you're wondering. There's weird times in there. You stop being tired part of the way in. Anyways, this is why that was such a pain in the butt. So a four-membered ring takes on what's called a puckered ring. Okay? And so see how it's slightly puckered instead of being flat? And that's actually reducing that ring strain a bit. But what it does is, yeah, it reduces it, but it's still mostly eclipsed. See that? You're mostly eclipsed. You're not really staggered, are you? Yeah. So even taking on that puckered configuration, it can't quite get away from being eclipsed. It's mostly eclipsed. Okay? It makes it very high energy, very unstable, very easy to react. Okay. This one here is cyclopropane, and there's just nothing you can do with cyclopropane. It is a flat ring because there's only three things, right? If you have three dots, that's a plane, isn't it? It doesn't matter how you orient them, they're a plane. Okay? And so in a three-membered ring, all angles of the ring are going to be exactly 60 degrees with respect to those carbon-carbon bonds at the same length. And so you end up eclipsed. You can't do anything. It's always eclipsed. And so that highest point that we'd fall off of for every other carbon chain is our molecule. Okay? We have trapped it in that highest energy form. Yeah. So that's cyclopropanes right there. Can you find cyclopropanes? Yes. Yes. People make them, and they do last, for time, especially if you keep it cold. And so you can make temporary cyclopropanes. They'll be very high energy and try to react. Okay? And so they will go bad and react and do things. Now, ring strain, this can be calculated from our heats of our combustion, so we can actually combust the compounds and see how much energy they give off. And that tells you how much energy is in that ring compared to the normal compound. And so you can actually give that energy in the form of delta H naught if you have standard conditions, and you keep your pressure constant. And that's a combustion reaction right here. Okay. That's our normal combustion action that we might remember. Okay, so this is the heat of combustion for some different rings here. So here's the heat of combustion that we see for this 6-membered ring, and this is the one for the 5-membered ring. And so if we do this per CH2 group, we can actually divide that by 6, because that's the number of CH2 groups we have here. And what we see is that's like 615.1 kilojoules per mole. Okay. Now, if we were to look at that in comparison to the normal chain, okay, what we'd see is there's actually a zero difference if we were to compare that to the reference. Okay, this is going to be our reference from now on. So this is going to be the 0 degree difference. There's no real difference in these. There's no significant amount of ring strain. Okay, so if we look at the 5-membered ring, we do all that math again. What we're going to see is it's 620 kilojoules per mole per CH2. And so what we end up saying is, well, we take the difference between these, and that gives us a 5.4 kilojoules per mole difference. And so the additional ring strain there would be that 5.4 times the 5 carbons. That'd be the additional ring strain, which is that 27 kilojoules per mole. Okay? And that's where those numbers in that table came from. That's how you figure that out. Okay. You should have a very good idea of this. Yeah. Okay, so the equatorial bonds, these are going to line the plane that is roughly defined by the ring. And so if you take the plane and line as much of it as possible into a single plane, okay, So ring as much as possible in a single plane. The equatorial ones are going to be on that plane, essentially. Right? The axial bonds will be perpendicular to that plane. Okay. Can everybody see it okay? The green and orange? So the green ones jut out into the plane, and so they're equatorial. The orange ones jut out up above the plane, perpendicular to it, and so those are axial. Okay? As in like axis, right? Jutting out away from the plane. Equatorial like equatorial and planet. The green. No, all the greens. All the greens are the hydrogens. They're equatorial. Think of it a bit like a planet. And so right here we have the equator. And these are all on the equator. These ones are axial because they're perpendicular to like little axes on the planet. So axial. And there's one back here, by the way. You can't really see it very well, but okay. All right, so let's talk a bit about chair flips. Now remember, conformers are not permanently frozen in position, right? They can change. There's a certain population that's going to interchange between those conformers all the time. So chair flips are going to convert the axial hydrogens into equatorial and the equatorial into axial. So it's going to convert each of those and cause those to flip. Okay? Okay, so right here we have one of the chair conformers. When it does the flip, this goes to the head, this goes to the bottom part, right? Footrest. Okay. And so what you're going to see here is that the ones that are involved in this, they're going to switch which ones are axial, which ones are equatorial. Okay. So what's going to end up happening is our new foot right here. See how those are swapped? The one that was axial is now equatorial. Okay. The one that was equatorial is now axial. Okay. And so anytime you do a chair flip, it's always going to interconvert the axial and equatorial ones. Okay. So this right here is the energy diagram for the chair flip. This is actually our conformational interchange for this chair conformer. Okay. And so what we see here is that we actually have a multi-part process. So the chair conformers, the two different versions of it, are going to end up being the same energy. So we don't have any differences. They're all hydrogens and carbons. It's all the same. So what's going to happen then is you have the half chair. This is where this foot comes up and becomes essentially even with the plane of these 4 carbons here. Okay. And that's going to be your highest energy one. So that's your high energy barrier you have to overcome. So the next thing that's going to happen is because this became even with the plane, it's going to start interfering with the other carbons, right? We're going to start getting more ring strain. And so this is actually going to take on the conformation of what's called twist boat. See how it looks a bit like a boat, but it's twisted, right? Because it's trying to maintain those tetrahedral angles, right? It's trying to maintain those same sort of torsional dihedral angles we had before. Okay, so see how it's twisted? So like these are not even anymore. Okay. Goes like this. You can actually do this with your ring, by the way. If you make this model, you can literally just go like this, and it'll pop into this form. And it fights you a little bit. And that's because it has greater ring strength, right? So if you do this with a model, you'll actually get this automatically. You go here, it'll either fall into this direction or this direction on your model. And so you can actually do this very easily. Now, the twist boat, that's a stable-ish conformation. It's a high energy one compared to the chair, but it is a stable conformation, okay? And this right here is then the energy barrier between the different twist boats. So if you twist it one way, you get one twist boat. You twist it the other, you get the other twist boat. And going in between, you have the boat conformation, which is where they're even on both sides. No twist. Okay? That kind of making sense? And then when you go the other direction, so you have the other twist boat, you can actually, again, flatten one end, and then you drop down into the chair conformation again. And again, this is that large energy barrier. Notice it's symmetric because we're symmetric in our ring. Okay? Okay. Anybody have any questions there so far? Okay. All right. We got some conformers. Now, one of the reason that we have that strain on that boat conformation is you may have noticed that we're bringing both these flaps up next to each other, right? And so the things jutting off those flaps, they're going to start interfering. Kind of like a real boat if you did that, right? You have the mast and they'd start hitting each other, right? Okay. And so you have the axial positions right here that are up above that ring. And they're going to start clipping each other. And this is called the flag pull interaction. Because literally it's like the flag pulls on a boat, right? Has anybody ever seen that, by the way? Where you have a relatively small sailing boat, and then they have little pennant pulls, and it hits a really large, big wave? There he goes. No? Okay. That actually happens, by the way. It's the same thing here. Apparently, whoever did this was probably a sailor or somebody not like boating. Anyways, flag pull interaction. This right here, by the way, notice that these are going to be eclipsed. These are these sides here. Can you see that those are going to end up eclipsing each other, aren't they? And so we end up with the eclipsed conformations on those carbons. And so this is very high energy. It ends up being quite high energy, and it's not particularly stable. It is going to fall off onto these two. But the interesting thing about this area right here is, in comparison to the twist boats, it's not that much higher energy, is it? And so you actually get a pretty quick interchange between these two. Okay? This is still not stable, though. It's the high energy state. It's going to drop off there. That is the energy barrier right there. And that would be your activation energies, right? They wouldn't be anti. Well, there are some parts of it that will be anti. Anti is something you do down a Newman projection. Okay, and so you have to be anti with respect to. Okay. But there are a few parts that'll be anti in a twisted boat. But for the most part, you have a lot of eclipsed on a twisted boat, or nearly eclipsed. Yeah, which is why you have that big energy difference here. Yeah. This one's going to be your closest to staggered and anti almost everywhere, which is your chair. That's why it's the lowest energy one. Okay. But it will be a lower energy than this. So it is like a stable conformer. And if you have the right temperature, you'll actually have a decent population of this. So, or in fact, there is one of the things in my dissertation that the most stable conformer is actually the twist boat. And it's because of the substituents on it. They want a hydrogen bond. And so they like twist the whole boat so they can hydrogen bond. Yeah. Anyways. I know. You can comb through my 27 publications and find it, okay? Now, chemists have devised a shorthand notation for drawing chair conformations, and this is that shorthand notation that helps you out here. So what we typically do here is this would be the chair conformation right there, right? Everybody good at that so far? Okay. Now, whenever you're drawing this out, one of the things you need to remember is you need to make this bond here shorter. Okay? This bond over here needs to be a bit longer. And then you come across with a longer line, shorter line. And then you come up. Okay? And so when you draw these, it can be a little challenging at first. You may want to practice a few times if you're going to try to draw them by hand. Okay? I would recommend drawing them by hand at least a few times. And so, see how I did that? It's a perspective drawing, right? And so this longer, short, longer, shorter. See that? And then this one shorter, longer. Okay? Okay, so that's how you draw those out with your hand. The other part of this is note that these would be in and out of planes, right? And so this would be a pain in the butt to actually draw this out every time. Can you imagine that? Having to draw that out every single time. Okay, so the shorthand that there is to help you out on this and actually drawing these out is that we actually use that perspective to kind of help us out in terms of what's axial, what's equatorial. Okay? And so see this one here, this is coming up. See that? This one's jutting out. Okay? Can you see the kind of the plane is right here? Okay? Okay. And so this is our axial, this is our equatorial, right? And so you come up and then jut out. Whenever you're doing these. Okay. Now, let's talk a bit about the ways of quickly identifying which is which. There's some tricks you can play. Okay. And that's by the fact that you really need to just identify like one hydrogen on these 6-member rings. Once you get your first hydrogen that you figured out, hey, this is axial, this is equatorial, the rest of them fall in place pretty quickly. Okay. And you can use this to help reinforce, did I get it right? Right? Okay. So what we want to do is we have these bonds here, right? And everybody's good with that so far? Now, by convention, these carbon-carbon bonds towards the bottom of the ring, these are actually interpreted as being in the front plane of the paper. So these ones here are coming out towards you. Okay? These ones in the back are going away. Okay? And that's by convention, so you can easily look at it and go, oh, this is what it is. Right? Is everybody okay with that perspective so far? Okay. Okay. Don't be super down on yourself if you have difficulty understanding this just by looking at two-dimensional pictures. Get a model kit and actually make the model. Okay? And then this will make more sense. This is a separate IQ, by the way. There's three-dimensional IQ. It's one of the categories in IQ testing. And so people that are strong in other places sometimes are not strong in this. Okay? So it can be a weak point for people. Now, so again, the bottom of the ring are going to be interpreted as being in the front plane of the paper. That's the one that's on the furthest part of the bottom here. And that's coming out towards you. Okay, now axial bonds are going to be perfectly aligned, and they're going to alternate up and down throughout the ring, and they actually have to alternate each position. So if you have one up, that's your axial, then the down is axial in the opposite direction. Okay? And then this one's axial, and it's in the upward direction. And axials always overlap, always are going to alternate back and forth. Now in a 6-membered ring, it's even, so that it wraps back around. Okay? And it works perfectly. Everybody see it okay? So when you're doing your axials, what you want to do is you want to go ahead and do the axials first, because those ones you want to define, everything else is going to define off of that. Okay? And you can literally just go through down, up, down, up, down. Everybody see it okay? And those are all my axials, aren't they? All right. And by definition, because we have the anti, right? They have to be alternating up and down. That's actually your anti. And so right here, then we have our equatorials. And again, these also have to alternate. Okay? Now, the equatorials are the ones that are, if you're going to have trouble looking at something and going, this is equatorial, equatorials are going to be it. Okay? Like, looking at this without the axial, how the hell do you tell that's equatorial? It's kind of difficult, right? Now, you can tell because it's not perfectly up and down, right? It's slanted. Okay? And by definition, by convention, you always draw your axials perfectly perpendicularly up and down. Okay? And then all your equatorials, slant. Okay. But if you mess up, this one looks pretty close. So your equatorials are going to be the ones that will confuse you the most. But if you've already put in your axials, yep, there's only one position it can be. Okay? So this right over here, I just put something like that, right? This one over here, I just make sure it's angled, right? That's all it has to be. If I don't have space for it to angle that way, I angle it some other way. Okay? But as long as it's angled, that is always my equatorial, isn't it? Right? My axials are always the ones that point up and down, aren't they? Okay? Okay. Is that making more sense? Yeah, so it actually becomes super easy to figure out which is which, right? So what do you always look for first? I'm trying to figure out my axials, equatorials. What do I always look for first? Axial. Look for my axials, right? That's going to tell me everything else, okay? Only if once I've figured out my axials am I going to look around for an equatorial, okay? Okay. Now, the chair conformation, if we look for a parallel bonds in the shorthand notation, we can actually see that we end up paralleling these bonds. So whenever you draw this out, you should always end up with a paralleled structure because it's a symmetric structure, right? And so, for example, these two are parallels of each other. See that? Not going to be perfect. Like this was done with a program to make it perfect, but it's going to be very close. Okay. Okay. And so, like all the axials are all parallel because we very specifically designed them to be that way, right? And then the equatorials, which you should see is this one and this one. These are on the opposite sides of the right. So they're parallel. These ones, opposite side again. So they're parallel. Okay. Although bonds are on opposites, are always the parallel ones. Okay. Making sense so far? Very good. Okay, so this is the step-by-step method to draw out this. I personally like doing the angles first, but I also took like 4 years of art and was told I should have been an artist and sold things for $400, art pieces. So maybe I should have. Can you imagine me as an artist? Yeah. You can? Oh, wow. Okay. Well, thank you. I think. But most people apparently have an easier time doing the parallel lines first. Okay? It is not easier for me, I'll tell you that. But you can do the parallel line first. You can see it is not easier. I find that much harder. Okay? I find it easier to do the triangles first and then go from there. But each your own. Everybody's going to be a little different there. Okay? This is how you do it with the parallel lines. You put in these parallel lines first, which is not hard. Those ones are pretty easy. The hard ones for me is to get the angles to actually connect here when you do that. Okay? But again, you do parallel lines, and then your next set of parallel lines. And then you put in your head. So you need to figure out your axial for your head. Notice that's where I started here as well. Okay? And then you put in your alternating axials. It'll always reconnect around. If you have a 6-member ring and you try to put in an axial going downwards over here, what happened? Yeah, it's not right. I need to go back through and do that, don't I? Because we're even. If you alternate, you always come out the same thing, right? Okay. So you could go around this infinitely, and you'd always end up with the same lines. Okay. Get all your axials in place. Once the axials are in place, you're going to put your equatorials. Your equatorials are going to be the ones that are going to jut out along the plane of the ring. Okay? Do they have to be absolutely perfect? No. As long as you have your axials perfect, your equatorials will always be opposites. Okay? But they need to not be straight up and down. All right. Anybody have any questions there? In this one, cyclohexane, yes. But they could be bromos, they could be. Okay? We could have CH3. Yeah, they could be any. But in so far, we haven't done anything else. We've just done. Right. Yeah, that's why they're empty spots. They could be any. Okay. Now, the conformers for the monosubstituted cyclohexanes, we finally get something on those spots. This is our first one. We'll do a methyl group. Okay. And so this is going to be the monosubstituted cyclohexane. Typically, by convention, you put that monosubstitution on one of these header foot positions, typically the head position. Okay. That first one that you draw. Just because it makes it easier to draw the rest of the stuff. Okay. Now, the most stable position is actually going to be the equatorial position. You'll notice that these two structures are very much not equivalent. Can you see that? Like this one overlaps heavily with these, doesn't it? Yeah. And so you're probably already going, oh, that's some steric strain. And you are right. That doesn't look very comfortable, would it? Okay. This, on the other hand, is the equatorial. And so it's laying out, it has plenty of space, it's not having a lot of strain. Right? And so very much not equivalent. This actually causes you, when you have monosubstituted cyclohexanes, to actually have different chair conformations that have different energies. Okay? Bless you. All right, now, two non-equivalent chair forms are going to be conformers of each other. They're going to be different conformations of this ring. The monosubstituted cyclohexane is going to be lower in energy, more stable. One, the substituent occupies the equatorial position because it has more space for less steric strain. Okay? The axial position is going to be higher energy. Bulkier groups are going to favor that equatorial position on your cyclohexane ring. And so the bulkier the group, the more it favors it. If you have a very bulky group, it's going to heavily favor this. Okay? And you can get some very large energy differences. All right, so this right here is several of the reasons for this. And so what we can see here is when we do these Newman projections, see how this is actually the gauche conformer? Yeah. And so we end up with the gauche conformer there, doesn't it? And so that's part of that energy difference. We end up in the anti-conformation here. See how it's on the opposite side of this one? And so the other part of that energy difference is actually the 1,3 diaxial interaction, which is a steric strain. And so these are the 1,3. See how it's the 1 and 3 positions that interfere with each other? The larger the group on here, the more this interference is going to play. Okay? When we have it this way, see that the 1,3 diaxial can't interfere with each other. We're on opposite sides of the ring. So we completely avoid that 1,3 diaxial strain. Okay? And that's the equatorial column. All right. So let's go ahead and look at some of the effects of chair flipping. This is one of the reasons why we had to go into so much detail in the chair flipping, by the way, is because this becomes extremely important as we add substituents off this 6-member ring. Okay, so the bulkier the substituent on that cyclohexane ring, the more favored that chair conformation is going to be. That puts it in the equatorial position. The less favored it's going to be in the axial position. Okay, so if we just have hydrogen here, we get 50-50. They're equal energy. Neither one is more energetically favored. Okay, when we get an OH, you can see it all of a sudden goes up to 81% ends up in the equatorial position, and about 18.7% ends up in the axial position at room temperature. And so already we're seeing a very large difference, right? But we make that even bulkier, and what we see is it drops off even more. And by the time we get like a tert butyl, it's a really bulky group, and we end up with essentially all of it ends up in the equatorial position. You'll have very, very little of it that ever ends up in the axial position, but you will have some. Okay? And so it's a pretty large difference in energies there. All right, now, the chair flip does not switch a substituent from one side of the plane to the other. It switches whether that's an equatorial or axial position, right? So it literally flips which positions it's in, right? For equatorial axial. Or another way of saying that is it flips the chair, not the person, right? Not the substituent. The substituent stays on the same side of the plane. Now, the cis-trans relationship between any pair of substituents on a cyclohexane ring is going to be independent of your chair conformation because, again, they don't change whether they're on the top or bottom of the ring. That doesn't change, right? Think of it a bit like this. You have your hand. Let's say we have a ring on the hand. It's pointing upwards, right? Does closing my fist cause the ring to start pointing inside my hand? No. It's the same thing as a chair conformation change, isn't it? So things that are axial, things that are above the ring are not going to change. Things that are below the ring are not going to change. But whether it's axial or equatorial, that's going to change, isn't it? Its orientation is going to change. Okay? Now, the substituents that are cis to each other on a cyclohexane ring are going to remain cis after a ring flip, chair flip. It's not going to change any of that. Cis to each other, still cis. Trans to each other, still trans. Not going to be affected. The cis-trans relationship of any pair of substituents unaffected by that chair flip, of course, it's going to be oftentimes more convenient to represent substituted cyclohexanes using what's called Hawthorne projections. And I'll show you a Hawthorne projection in a second. But remember that it doesn't matter if we represent the cis-trans in a flat ring, in which chair conformation, none of that matters, right? Because cis-trans is not affected by the chair flips, okay? It changing the conformation does not change the cis-trans relationship. Or another way of thinking of this is we have conformations that change back and forth. We have stereoisomers, in this case, that do not change back and forth, right? The cis-trans relationship. Okay, these are Hawthorne projections. You've already seen a few of these. And it's where we basically draw the ring so it looks like it's jutting out towards you, right? So it's a flat ring in your perspective going away from you. Can everybody say okay? And that lets us represent the stuff that's on top of the ring and the bottom of the ring very easily. It makes it much easier to tell, hey, these are on top of the ring. This is top, bottom. Okay? Whereas this one makes it a little bit more difficult to tell, which is just the normal, we're representing this ring as being flat in the paper. Okay? All right, does anybody have any questions there? Notice we're just rotating that ring 90 degrees so we can get a different perspective. Okay, now let's go ahead and talk about this in terms of the Hawthorne projections and doing our chair flipping. So every substituent on a cyclohexane ring is going to favor an equatorial position rather than axial position. It doesn't matter if we currently have that carbon written as being the head or in the middle of the base part of the chair. Like, that doesn't matter. Okay? All of these positions in reality on that ring are the same in terms of energy. Okay? There's actually no difference. You can actually draw it with different perspectives. And so this right here is going to be the most stable when we have the cis form here in the chair conformation, where these are both equatorial. And this is called diequatorial because both of them will be equatorial. Okay. Notice that's because they're on the 1 and 3. Remember that? They alternate, right? So this right here, if this one's equatorial on the top, then on the second one, this would have been axial, wouldn't it? And on the third one, this has to be equatorial here. Okay? And they have to be alternating same, right? On this 6-membered ring. Okay, so this is going to be our favored chair conformation, where they're diequatorial. Notice if we do a chair flip, it puts them both axial. And so we get the diaxial, and that's going to be heavily disfavored. Okay? And so that's the highest energy conformer right there. Okay, now let's look at this one down here. This is the trans. See, they're on opposite sides of the ring, and they're again the 1-3 positions. Is it okay? And so them being on the opposite side of the ring means that anytime you get one in the equatorial, what happens to the other? Axial, right? Has to be the opposite. Okay. And so when we get this one in the equatorial here, this one ends up in the axial. When we get this one axial, this one ends up equatorial. And so what we see here is they're equal energy. One of them's always axial, one's always equatorial, and so we'll always end up with an equal energy. So neither of these chair forms is favored over the other. Okay? They're both going to be the same stability, same energy, because one is always axial, one is always equatorial. These right here are what the models look like. And so this is the chair conformation with a model kit right there. This right here is the equatorial and sort of the upward position as we saw here. Can everybody see that equatorial position? Okay. And then this is the axial position right there. Right. So one of the things you can really tell with the model kit a little easier is look at this right here as being the foot. And then you have the base, and then you have the top position, right? The head. Okay. Okay, can everybody see that in that picture? Okay. Now let's look at this one. This one's the foot. Can you see that when we look at this one as being the foot, this becomes the base, this becomes the head? Can everybody see that okay? And so what we really see is that head, base, foot, that just was entirely perspective dependent, right? Literally, if you just look at it from a different angle, you're going to have head, base, foot again, right? And so the chair flip is where we're going to take these and we're going to flip each of these groups. Okay. And so we flip this, and what we can see is the equatorial here ends up being an axial, doesn't it? And this one here, which was axial, ends up being equatorial up. Okay, let's talk about constitutional isomerism and identifying the constitutional isomers. So again, constitutional isomers are going to be called structural isomers. That's another name for them. They're going to share the same molecular formula, but they're going to differ in the connectivity. Okay? And so you're going to have the same molecular formula. You'll have 4 carbons, 8 hydrogens, right? And so same molecular formulas for both of these. Definitely not the same names, are they? No. And that's actually kind of an easy litmus test to figure out, are these constitutional isomers structural isomers? Is if you name them the same, they're probably constitutional isomers, assuming you did the naming right. Okay. If they would not name the same, they're constitutional isomers of each other. So if they're named the same, that's going to be they're the exact same molecule. Then maybe they're stereoisomers, but they're the same molecule. Okay, and they're not constitutional isomers of each other. If they would be named differently, they'd be constitutional isomers. If their molecular formulas would be different, i.e., you don't have 4 carbons, 8 hydrogens anymore, then they're definitely different molecules, right? Okay, so again, these two right here, these molecules are not going to be constitutional isomers of each other. Okay, does anybody know why? I mean, they look different on the paper, right? Yeah. These are conformers of each other, aren't they? Yeah. And so all that's happened here is this right here has just been rotated. Okay. And so you just rotated that. And that's all that's happened. It'd be like having a chain where you just moved one part of it over. No. It's not a different molecule anymore. It's not a constitutional isomer. It's just different configuration, right? And so you do have to be careful here. And if you went through naming this, you'd pretty quickly realize these have the same name. Okay? They'd name the exact same. Okay. Now, notice that I'm starting to build like a flow chart. See this? And that's what I want you to start doing. I want you to start building yourself a flow chart in your mind. Okay? So, same molecular formula, different in some way. Isomers. Do they have that same connectivity? No, they don't. Well, that means a constitutional isomer. Am I over time? No, a little bit. So, some of the rules for identifying constitutional isomers. For each molecule, identify the parent chain or ring. Notice these are the rules for naming. Number the carbons in the chain or ring. Make sure that the carbon atoms involved in double or triple bonds receive the lowest numbering. Literally go through the process like you're going to name it. Okay? You may want to just name it just so you're easier for you. But you don't technically have to name it completely as long as they match up the same naming. And so you go through the same process to name it. And so like these right here, if we started doing that, we go 1, 2, 3, 4, 5, 6, right? We find the longest chain is 6 each time. And then you go, well, this one's on the second, that's a methyl. This one right here is on the fourth, that's a methyl, isn't it? And so they're the same, aren't they? So those are not constitutional isomers. Okay. All right, so saturated molecules contain only single bonds and no rings. And one of the ways you can help yourself figure out your constitutional isomers, if you have a constitutional isomer, if you don't, is with what's called degrees of unsaturation. Another name for that is the index of hydrogen deficiency, but I have never actually heard of anybody using that name. So it is historically correct, I know that for a fact, but everybody says unsaturation. So I don't know what to say about that one. Saturated molecules are going to contain only single bonds, no rings. The molecules that contain double bonds, triple bonds, or rings, these are said to be unsaturated. Everybody ever heard of saturated fatty acids, unsaturated fatty acids? That's what an unsaturated fatty acid is. It has a double bond in it, at least one double bond. Saturated fatty acids don't have any double bonds. So this is the same thing. They just don't apply it rigorously in biochemistry. So the index of hydrogen, IHD, of a given molecular formula is going to be half the number of hydrogen atoms missing from the molecular formula of an analogous, i.e. the same number on type of each non-hydrogen atom, molecule. So if you had a saturated molecule, it's half the number of hydrogens are missing. Okay? And the reason it's half the number of hydrogens are missing is because when you have a double bond is going to take 2 hydrogens off of 2 carbons, right? And so you want to figure out how many degrees of unsaturation, i.e. how many like double bonds you have. Okay? How many rings do you have? How many triple bonds do you have? So remember that each double bond contributes 1 to a molecular's IHD, that hydrogen deficiency. Each triple bond ends up contributing 2 because it has 2 pi bonds, right? And each ring is going to contribute 1 because it comes back together and takes up that extra bond, doesn't it? Okay. And so this right here are different IHDs. Notice the number of pi bonds directly correlates typically alongside the number of rings. Okay. And so if we count up our number of pi bonds plus the ring, that gives us our IHD right there. And that's 4 plus 1 equals 5. Everybody okay with that so far? Okay, now if we have a double bond, it's 1 pi bond, right? If we have a triple bond, that's 2 pi bonds, so that's 2 to the IHD. Okay? And so we count up our number of pi bonds again, we don't have any rings, and so that directly tells us our number of IHDs. This one has 3 rings, 1, 2, 3, right? Okay. And so it's going to have 3 IHD from the rings, and then 2 from the pi bonds. And that gives us our degrees of unsaturation. Okay, so why should constitutional isomers have the same IHD numbers? Can a constitutional isomers ever have different numbers of IHDs? Yeah, they would have different formulas, wouldn't they? They'd have different hydrogens. Exactly. Perfect. Yeah. So you literally just can't do it. At that point, they're just totally different molecular formulas, aren't they? And that difference would be the hydrogens there. And this is some different examples. What is this IHD number for this one? This is naphthalene, by the way. Anybody have grandparents that have like that moth ball smell going on? I don't know if that's still a thing. Is it? Okay. Then this is naphthalene. That's the mothballs. Okay. At least one form of the mothballs. There's a few others. Okay. Everybody ready to give those IHD numbers? Dun, dun, dun. Okay, so we count up the number of pi bonds, right? And that's the first easiest one to do. So 1, 2, 3, 4, 5. And then we count up our number of rings, and so that's 2. And so all together, 5 plus 2 is 7. Very good. Okay, you can calculate this from the molecular formula. So remember those formulas I kept giving? If you have a saturated alkane. So what is that number for a saturated alkane? Well, it's always 2N plus 2, right? So you take your number of carbons times 2, then plus 2. By the way, this is where you'll need your calculators for this next test, in case you're wondering. I know, it's super hard math. I will give you one formula that's a little harder, but that's a while. Okay, so let's say we had a number of carbons here. Again, if we look at this, these are called methylenes, by the way. They have 2 hydrogens on them. And so the majority of carbons in a carbon chain have to be methylenes, the CH2, right? And then the plus 2 was always the ends, wasn't it? And so if you make a ring, those are the ones that actually disappear. Right there. That's the plus 2. Okay? And so there's actually corrections we can then make for each of the nitrogen, oxygen, and halogens. Halogens just directly replace one hydrogen, right? Oxygens actually don't change the number because an oxygen just ends up slotting in. Like when you add an OH, right, you still have this same number of hydrogens, don't you? And so you end up just slotting it in. It doesn't change that number. And nitrogen actually adds a bit to it because you get another spot you can put a hydrogen, right? See how that nitrogen added another hydrogen to it? So that's plus 1. Okay? And they make very nice logical sense. I'm over time by a minute. Sorry. You all have a wonderful day. I'll see you next time. I'll be releasing the exam sheets on Wednesday. Okay? You all have a great day.